because the CRT is attached to the chassis, I just kind of came up 4 blocks of wood and some pipe insulation rolled up to kind of support the whole thing. And I can get underneath once we get her going. I can see some of the raster. And just kind of going back to where we were, what we found when we had it running. This multi-section cap right there, that's C2. That's part of the audio output circuit. That was getting really hot, and so clearly that has to be changed, but there's very little room inside there. C2 is that thing way in the back there, right back there. So what I think I'm going to do is I've been thinking about this for a little bit. I'm going to grind these rivet heads off and pull this connector down. That is the connector for the bass and treble controls. And also, when we had it running, we saw a raster, and there was a fold over on the bottom. We had a vertical sweep, but it wasn't right. As I mentioned, there's a couple of these bumblebee caps. These are in the vertical circuit, these two for sure. And there's a crack on one, if not both of them. And I think that's a good place to start also. So maybe we'll start with C2, replace that. Cut that can off with a hacksaw and go in from the top. I think then that's a cleaner way to do it. It's a 4-section cap. And also this is C1. This is another multi-section cap that is part of the vertical circuit. So if we go over to the schematic, what we have here is here's the audio output section. So this is part of C2, C2, and then over in the power supply section, there's another section of C2, and then the 4th section of C2. So it does a lot of things. And then also in the power supply section, C1 is part of it as well. And I believe over here right there, C1 is also part of the vertical circuit. So that's one of the bumblebees, and I believe this one, that's C3. This one is one of the bumblebees also. I think that one, this is a 1,000-volt cap. Some of the component positions chart, tubes and key components. It's the bottom view there, and that sort of matches the way I've got the chassis oriented, so it makes it a quick. So I'm going to get started while they're blowing the leaves off of our neighbor's driveway. Well, that was easy. Those 2 rivets came out in seconds, really. I just used a Dremel with a bit like that, a punch and a hammer, and knocked it out. So you got to make sure that you find, if you do something like that, make sure that you find the rivets, which I did. You don't want that floating around in the chassis. So I pulled the wires that looped through the top of the chassis. This is, like I said, the connector for the bass and treble tone controls, but it gives us enough access to get in there to deal with that, recapping that. So what I think I'm gonna do is just get in there with a hacksaw. I might need 2 hands. Oh, that was easy. That took like literally less than 30 seconds to cut this thing off. And it's good. Now we have this reference to what the symbols and the values are. But this, golly, this is really dry. There's nothing in here. Anyway, that's what it is, cut off. And so what we'll do is we'll just get in there with a Dremel or something and just drill some holes through there and shoot the component leads down from the top. Yeah, the price of electronic components is just going through the roof. So I ended up taking a chance and going to eBay, and I found a gentleman who has an online store, Love Music and something, and each of these caps are 99 cents, as opposed to some of these highfalutin fancy pants caps by somebody else, Nichicon. These are like $3, $5 a piece. They're really, really expensive. So I like Mauser very much, but I just thought I'd give these a chance. These are sort of maybe off-brand, if you want to call them that. I don't, well, when we get into it, we'll talk a little bit more about it. But okay, so before, I just wanted to confirm which leads were which. There's the half circle, the square, the triangle, and then the dot, the non-annotated lead, and they all have different values. I've made a note up here on my schematic as to the relative position of them and their values. So confirming that, even against the what's on the can, all that matches. The capacitance and the voltage values and the symbols. So that's all good. And I'm just gonna take my Dremel tool and quite literally just shoot holes in here. Doot, 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 doot. And then we'll just drop the leads in from the top. Get this out. And there's just one little section here, but yeah, right there, all the holes. Easy for the leads to come through, and then we just solder them to the terminals here. So be cutting off the back of the capacitor. It's no longer a capacitor, so we simply just have holes coming through a piece of Bakelite or whatever this is, and the components go on top. I put two inside. They're small, 50 at 25 volts and a 4 at 150 volts. And then on the top I put the big one, the 4 at 450, and what is the other one? It's like 4 at 350. So yeah, that worked out pretty well. I brought a, hard to see this, I brought a ground lead. Well, so that worked out pretty well. I brought a ground lead from here, soldered this to the chassis and brought it up. Next step would be to put this here, back up. If I didn't make a mess out of these things, I don't think so. I think it worked out pretty well. And I've got enough room here in case future holds changing some of these capacitors out. There's enough room on this ground to just go where I need to go with it. Okay, what's next? This side, the vertical side of the chassis. C1 up there, and some of these bumblebees. This one, that one also. So looking again at this next capacitor, this is C1, and it's marked in the typical triangle, square, and half circle to denote its different capacitances. However, it's really strange because on the SAMs, it just says A, B, and C, so don't exactly know which one is which. And yeah, we could trace the wires. We'll do that also, but I did notice something just a second ago, that this, look at this. This is not soldered on. Look at that. So, I'm going to determine what that was for. I'm curious. I'm really curious about that. That is just strange to see workmanship like that. That's opened up. So, okay. Well, I'm going to track some of these down. In this particular one, we can go look at the schematic, and I'm not even sure if this is a crack in this resistor. I'm going to leave it alone for now, but keep an eye on that. What is that? Brown, green, orange. That's 15K. We looked at is 15K 2 watt, and that goes to the B plus, the 245 B plus And over here is section C1, and that is an 80 microfarad. So let me look at this, double check, but where is it here? This half circle would be 80 microfarad. So I'm going to just snip these off. We're going to recap this. I'm going to snip these off and read the capacitance of each section and get an idea, just to double check that we're doing the right thing here. Well, this was just not soldered on. It's bizarre. Just not anything there. And that was it's this. Yeah, that's a 40 microfarad. Weird. Checked it with the meter. Let's do that again. Yep, 40. Well, I've got this other multi-section cap recapped. I just snipped off the lugs on these this capacitor, and I mounted one of the caps here. There's only 2 leads going to it, and I soldered it to one of the grounds there. And then this other lug, this was the 80 microfarad section, had a big gaggle of wires, probably 5 wires. So I snipped it off. I'm going to put some heat shrink on it, and I mounted a terminal strip here, and this is supposed to be 80 microfarad. So I doubled up 2 40s and soldered down the ground, but I also ran a double check ground to this point here. So C1 is done. I'm just going to throw some heat shrink on it, on that big glob of stuff. And yeah, it may not look good, but it's totally functional. And I just want to get this running, and then we can see what happens next. So we have the electrolytics changed out, and so I wanted to just give it a test to see if we have a raster. And however, this is the Space Command chassis, and it needed to be in there for this. It's just a jumper. So up here on the schematic, it's right here. That goes to the remote chassis. So at least for now, the easiest thing was just to put this up on the bench and use it as a jumper. So, okay, well, let's just bring this up slowly. I don't know if we even need to bring it up slowly at this point. The electrolytics have all been changed. We just want to see if we have a raster. I'm already hearing some live from the speaker. Oh wait, and I even hear vertical. Oh, sure enough. Okay, so we have a raster, and I hooked up a little speaker. You can hear that there's sound anyway. Okay, well, and then this is the contrast control. Yep, that works. And then this would be brightness, I think. Oh yeah, so that's all the way down. All right, so we clearly don't have a signal. It's not hooked up to anything. This is the IF connector front that would go to the tuner. So we have a raster, that's great, and it seems to work. All right, so I might as well pull the tuner out of the cabinet. Might as well, and I could try sending a IF into here, but let's just get the whole thing out and make a mess of it. Well, this is quite a setup, but here we have it all. Start on this end with, we have a variac and kilowatt meter. We're setting it at about 116. The Sam said that the nominal voltage that things were measured at was 117 volts, so we're there. Here's our tuner that we just took a look at. Two new tubes. We're connected from the RF input of the tuner to the RF output of this the signal generator. It's a Sencor VA48, and it's a great little thing. And then we are set at our RF level is set to normal, and we have we're set at RF output VHF channel number 7. Turn our sound on, and we have a crosshatch pattern, so that should feed RF channel 7 into here. I think I am on channel 7 on here, best guess for now. And here's our remote chassis that it serves as nothing more than just a jumper cable in here. And everything else is hooked up. There's a speaker, and back here would be the tone control. We don't even know what we're going to get when we turn it on. And then here's our on-off volume. Measuring stuff. I've got my trusty old B&K vacuum tube voltmeter. It's the 177. I do like using that for measuring grid voltages and things like that. It's got to warm up. It doesn't put quite a load on it as some DMMs. And then I also have this. Also, just got this. I like it a lot. Energizing. Oh, look, the tuner light works. Well, that's good. We hooked that up correctly. And yeah, current draw is coming up. An amp. Hey, I hear something. Oh, look at that. Well, we do have a picture of some kind, so I don't know if you get this, but the face of the CRT is right here, and we're just looking into a mirror because there wasn't really any other way to do this. But we have a picture. It's rolling quite badly, though. Doesn't really seem to want to lock. No. Doesn't want to lock so much. But, hey, how about that? Brightness and contrast. Contrast. Brightness and contrast. Yeah, pin 4. Should be minus 25 volts. It's 1, 2, 3, 4. And what do we have down here? We have minus 18. And I would bet that as you change the vertical hold, that number will move. So let's go ahead and not to go too much further into this, because we know that we've got to do a little bit more work. Do not want to check the pin 2, that's the output. Do not measure that, but over here, pin 5 is the plate of the oscillator section. We could check that. It says 115 volts. Pin 5, 1, 2, 3, 4, 5 should be this one. And that is pretty close, 109. And so yeah, this looks like a pretty healthy thing. Let's start with these caps. These bumblebees are suspect. Just thought I'd take a couple of readings before I got into recapping this vertical circuit. And wanted to look right here at, that's the vertical output tube. Pin 1 is the grid, and that's the waveform up here. And at the grid we should see a -1 volt, and the signal travels out of the oscillator, travels through this 0.1 cap, that's the one that's in question, and through a 1,000 ohm resistor and to the grid. And if that cap was leaky, we would probably see something much higher, probably a positive voltage there. And then above it we'll also, we're not going to measure that, but that cap is a 1,000 volt cap. That's going to be replaced as well. And then we'll also get to this one and this one eventually. But we'll start with this one. Just wanted to take a reading, wanted to take a look at that waveform, see how it looks. And this is super convenient. That's pin 1 of the vertical multi-vibrator and output tube. And so we're just clipping right on to that 1,000 ohm resistor that we just saw on the schematic. And this particular cap, that's the one in question. It's hard to see the color code on it, but that is a brown, black, yellow. So that would be 1 0 followed by 4 zeros. So 1 0, 100,000 picofarads. And then you move the decimal place from right to left 6 points, and that would give you a 0.1 microfarad. So these are all in picofarads. All of these bumblebees, this would be in picofarads also. 3 with 3 zeros, so 33,000 picofarads. Move the decimal point 6 places to the left, right to left, and you end up with a 0.033 microfarad cap. And then the next color band would be the voltage. It's 400 on this cap. That would also be 400, the yellow band. And then the band after the 3 numerators would be, that's the tolerance. White was 10%, and I really can't see very well what that is. Looks like something else. I'll look it up. I'd imagine it'd be a little bit tighter tolerance. And then this one is a 1,000 volt cap that's in the plate circuit. So we'll get to that in a second. But let's just take a look at this. This is the vertical circuit, and I've got our handheld scope. Sometimes it works. And we've got our DMM. And we have our vacuum tube voltmeter. So I've got the grounds hooked up to the 2 multimeters. Let's just take a look at this with our vacuum tube voltmeter. We're on the 50 volt scale. That's 0 to 50. And we should see a negative voltage, which means, and we're on the positive scale. So if we have a negative voltage there, it'll go down. We can just check an adjustment. Or if it's a positive voltage, it'll just display what it is. And whatever is displaying in terms of voltage might indicate or will indicate the leakiness or not leakiness of that particular cap. So let's take a look at this. Let's fire it up. I've got everything turned on, warming up. We're at 116 volts, and we'll just see if we get any activity out of the scope. You should start to see something as it warms up. There we go. Look at that. So that's our vertical drive, and that waveform looks pretty darn good. That's our waveform up here. That's our waveform. That's where we're at. So let's take a look at our voltage. Pin 1 of the output tube, the grid of the output tube. We've got a nice looking waveform. So let's, once again, beautiful waveform. Let's disconnect this. Super easy with this, super easy being right there. And then let's take a look at our vacuum tube reading, vacuum tube voltmeter reading. So this should give us, oh, look at that. That is a positive 25, 26 volts. That should be a negative number. So that cap's super leaky. And let's change that first and see what happens to our picture. Just as a reference, this is our crosshatch. We really can't achieve sync. Something's up. So we'll start by changing that first. I snipped that first capacitor out. This is a point one that's in the grid circuit of the output tube. And just for fun, let's test it. I wanted to see. I don't have a leakage tester, so I can't test its leakage. But I would assume that this is going to have pretty good capacitance, regardless, at least the way it tests. Huh. Nope, not even close. Look at that. An ESR of 44 ohms. And its capacitance is 232 nanofarads. So that's odd. From nanofarads to microfarads, you move the decimal point 3 places from right to left. So that's a 0.23 in terms of capacitance, and ESR of 44. Yeah, this isn't even a cap. So sometimes, occasionally, you can have luck getting into these solder cones on these Zenith chassis and insert the component lead right into the solder cone once you heat it up. But you've got to really get access to the back of the set, and there's just no good way to do that here. So, you know, I'm gonna J-hook these in. That's the way to do it. It'll be a perfectly fine mechanical and electrical connection. Some things you can get at and some things you can't easily. And there's a bunch of other caps that now that I have some of these removed, maybe I should just change them before I make the space uninhabitable again. Let me see. Well, I've got part of the vertical circuit done. As it turned out, just trying to get access to some of these components, it was really best to just sort of do more than I wanted to with one at one time. So I had to unsolder this from the tube socket. This cap was buried deep down in there. That would have been this cap, and I didn't have a 0.068 at 200, so I made it up out of 2.0033s at 650, put them in parallel, so it comes out to about the right value, just a little bit off. That'll be fine. And then replace this 0.1. That's a 104. 4 zeros at the end of that, plus move it 6 decimal points. That's 100,000 picofarads. Move the decimal point 6 points over to 0.1 at 630, and this one is a 0.22 at 630, also 630 volts. So that was good, and I had some success. Before I said that I never really have much success getting into these solder cones. This particular case, it seemed to work out all right. I was able to get everything, the old components out and the new components in fairly easily. So the thing is that when you resolder into the solder cones at Zenith, they must have used just a ton of flux. You can just see how much flux ends up here, and oftentimes it's really recommended that you try to clean some of that off, because I've found that some of these phenolic strips start to become conductive or capacitive, and you just start chasing your tail with a problem when in fact it's just the strip itself. So we're at a point where we should start it up, give it a try, see how it works. There's still others to change, but let's do that. I just wanted to put my gloves on. Before, I know I'm going to stick my hand in a live set, and I I don't know how much electrical protection insulation these provide, but in my mind's eye, it's worth a try. So, starting up. All right, well, we didn't destroy it. Let's see if we can get some of this vertical out. Well, still having issues. Horizontal hold. Is it better? There's still that goofy fold over. In order to get it to even for the sink to sort of work, there's a fold over at the bottom. But you know, we couldn't get this before, so that's a linearity issue. Different situation. The linearity control would be this one, and we'll get into that in a second. But let's go and let's replace those last two capacitors in the vertical circuit. And yeah, so that is better. That's definitely better than it was. It still isn't right though. All right, so actually there's three more. There's this 1000. There's this 33K, and then there's this one, whatever it is. So the 1000. Let's see. The 1000 is. The 1000 is in the plate circuit of the vertical output tube. 0.015 at 1000. We're going to change this out. This is the vertical output transformer, autoformer actually, and there's a neon lamp in this circuit, and I don't understand what it's for really, other than possibly some sort of voltage regulation or voltage clamping. But the output from the vertical output transformer comes across through the two vertical windings on the deflection yoke, comes down around here, so and it goes through a capacitor, resistor, there's this neon lamp, another resistor, and then it travels down to the a winding on the secondary of the flyback. So it gets a reference all the way over here to, it goes back to the horizontal sink circuit. So it's, and then finds ground right there. So I don't know what it does, but I do know that this lamp has to be changed. It's right there, and it's broken. It's been, obviously there's a lot of hours on this, and that just sort of corroded right through. So we're gonna change that, and we'll see what happens. I ordered a bag of these, and they're like $10 for a bag. So, and it's an NE2H. See if we can get this out gently. Yeah. There we go. So there it is. Pretty a lot of hours on this little bulb. So that might be an indication of the miles on this chassis. And then to get this, let's see if we can get this out like this. There we go. That came out easily. All right.
may not be as easy as it looks. Let's see how far we can get this thing down in here. Goodness gracious. There we got it. Here's my other hand. Go.
All right, so let's spark it up. Even though there's no signal passing from the tuner and into the IF strip, I still have all this stuff hooked up except for the signal path, just so that we keep our bias voltages consistent. But as I said, I'm driving a signal into the grid here of the video amp. Everything else has been disconnected back here at this point. The IF strip just doesn't pass a signal, and I think it's somewhere in here. Okay, so we're up and running now. I haven't yet looked at this with the set in an upright position, but you can see right there in the mirror the fold over. Now, what's amazing is that after changing a bunch of these resistors, we actually finally have some resemblance of sync, which we never had before. It would just roll. So we had some success in the, where is it, in the sync separator circuit here. Resistors that were bad, resistors that were bad. So let's take a look at what is at hand here. But that's our picture, and you'll see it start to drift. It'll start to roll. So we clearly haven't fixed all of those problems yet. But let's grab our scope lead, our probe. So I've clipped the scope probe on what is effectively the 1/2 of the primary, of the secondary that comes out of the vertical output transformer. And let's come over here to our scope. And that is not what that waveform is supposed to look like. It's just not right. And we'll turn it up a little bit in brightness. The deformation of the waveform is what that fold over is at the bottom. Get down here. Well, actually the scope has caused this too. But that fold over at the bottom, I just can't get it out any other way. So let's look back at this waveform. The peak to peak is, well, it's pretty good. It's should be like 180, 190, something like that. I love Zenith TVs, but when you start getting into a situation where you have all kinds of components, especially these resistors, because there's a group of resistors that they're very similar in value, and it just has to be a manufacturing error that just over time they went bad. To to go, so because you can't always measure the resistance properly of a resistor while it's in circuit, and sometimes you can and sometimes you can't, and when it doesn't seem right, the only way to verify if it's correct or not is to take it out of the circuit. But some of these Zenith components were so deeply buried in these solder pots and these strips, these phenolic strips with the solder pots on, that it made it really difficult, and you start destroying things, you know, just trying to get, let's see, where is this one? This particular one, I ended up, it tested okay in the end once I got it out, but I chipped it, and I swapped out these two capacitors, or 0.1s, yeah, 0.1, 400 volt, just because they're so darn big. They were just so big and in the way, and I couldn't get at other things, so I don't think those are bad, but replace them with something smaller. So let's get into these. But anyway, so my point of this is that we can unsolder some of this stuff. But this particular one, I've been in this particular solder pot about half a dozen times, and it's just making a mess out of it now. And also one thing, going to these components, you can see that they didn't cut the leads, so you have at least like an inch of lead that is inside the solder pot, and it's just huge. And they used a lot of flux in the solder, so you heat it up and the flux starts to ooze out. And I believe that over time, enough accumulation of that flux and it becomes conductive or capacitive. That was my experience on another set. So this is the vertical output transformer. This being an autoformer, I'm not really sure what to expect, but I replaced all the caps in the vertical circuit and I still have the fold over, and we're going to take that, and I don't really have any good ideas on how to measure it because it tests resistance wise. With an ohm meter it's fine. But when you put a load to it, a lot of these things, there could be some of the insulation inside. The windings could be cracked. It could be arcing inside, although I do not see any evidence of arcing in the picture, what picture there is. There's multiple problems with this set. So what we're going to do is put this one in. It just came in the mail the other day. And I was lucky enough to get this on eBay. It's a Thordarson, 9-to-1 turns ratio, and then it has the, well, just a little hookup diagram here. There should be a direct drop-in for the Zenith part. Well, I got one out, and to show you kind of what I've been doing to get things out of these Zenith solder pots. You can try to get at it from the top, but you don't usually have good access to get it from the top. So there we go. That one came out easily, but you can see how much wire is inside these things. A bunch, and it makes it difficult to get it back in too. Over here, we've got to get the green wire out from behind there. So good luck to us. I don't know. You know, I really didn't expect, and I don't know that this is even going to solve the problem. The fact that this thing works at all tells me that the vertical output transformer is fine, but I don't know that works that way. But every time you get into these things, you start destroying stuff. As soon as you heat all this stuff up, pull out these wires. There's only so many times you can do this. And I changed all of those capacitors. I made a mess out of it then. What did I just pull out? Oh, that needs to go in there too, doesn't it? This is the one of the leads for the deflection yoke. All right, note to self. connect that. And what do we want to do? Do we want to just tack this in here? Or do we want to just be bold and replace it? Let's check the resistance first. This is our blue lead. And we determined before that the impedance on that Thordarson is a 380 ohms or something. This I think is going to be a little bit less. Yeah, 207 ohms. And that's what it says on the SAMs, or approximately that. So this isn't quite the same transformer, but we'll put it in anyway and see how it goes. And then there should be 6 ohms between the green and the red. I know I shouldn't hold it like this. It's giving a false reading, but whatever. 10 ohms. Let's do this. 10 ohms. So yeah. Which is what the SAM says. Primary should be 215 and the secondary should be 10 ohms. So decided to just tack it in, because if it doesn't work, then I'm going to put the other one back in, and if it does work, I've got to dress this stuff up. This is the deflection yoke, and I've got to clean it up. So I just thought I'd tack it in, and it's pretty tacky looking. I should probably have gloves on, shouldn't I? Oh, all right, some other time. Throw caution to the wind. So we're gonna, when this thing starts up, we should know right away if there isn't any fire, but we'll see the waveform here, and that'll tell us everything. And we'll see the image on the mirror. There we go, there we go. Something's happening, something's happening. Something's happening. Oh no. Wah, wah, wah. We still have the fold over. Is this waveform any different? I don't think so, is it? What in the wide, wide world of sports is causing this to function like this? Like I said, the sync is terrible. No sync virtually. Some of them aren't right. Some of them have cracks in them. But these are resistors, except for this bulb. That's the neon bulb that was replaced. But some of these resistors are open, or they have a value that is many times what that should be. So this environment just didn't do well on a lot of these components. So I've changed all the electrolytics. I've changed all of the capacitors in the vertical circuit. And things do work. There's a raster, and the sound works, and we're gonna upright this and see what we get. So this is the picture. Super non-linear, folded over at the bottom. And by the way, this thing is a beast to move. Between the weight of the picture tube and the chassis and all the components on it, it's unmanageable, honestly. But that's the image that we have, and it continues to roll. Let me fool around with the vertical hold. According to the frequency counter, that's about right. That's about where it should be, because that's the frequency right there, 59.98. And well, it just kind of keeps rolling. This sync isn't right. The linearity is completely effed. And so this is, I'm just going to turn the linearity pot. You can get an idea of what doesn't work here. I mean, so we can get it to stretch out a little bit. And when we move the linearity, we change the frequency. So it's too slow. And then we go to our vertical hold and we try to 59, right around there is 60, 59.97 is our goal. So the vertical circuit is whacked out. And this pot, I know it works, but I wonder if it's working properly. I don't know. So I change the linearity and I can get it to lock. If we just start fooling around, if I stretch the linearity all the way to one side here, you can see how the raster on the top is just stretched out. So obviously somewhere back here where it actually can find sync is where it needs to be. But look at, and this control, the vertical linearity control, is turned all the way counterclockwise. So we have it, the fold over and the compression at the bottom, it's stretched out in the middle, and then it starts to compress again at the top of the picture. So let's look and see a little bit about some of these things. What controls do we have? We have vertical linearity, contrast, and brightness. So part of the good news is that the contrast control works again. That's the mega dynamic contrast setting. So this is like a push and pull situation. Goes back to the switch, and according to the SAMs, that is a normal and dynamic contrast control. So I guess in one position in dynamic, it inserts a 0.1 microfarad capacitor in there. Otherwise, it's out. Very simple thing. There aren't many things. Where am I? There aren't many things. Right there. There aren't many things attached to that switch. So looking at I think that's in normal mode, and I'm just bringing it up a little bit gently. And then the brightness there's plenty of high voltage. The high voltage at the second anode is, I don't know, it's like 25,000 and 23,000. It's plenty of juice. So going back here, we have linearity, which doesn't seem to get us where we want to go. Brightness and contrast work. This is vertical size. Vertical size, I'll show you that. Vertical size control, we're all the way counterclockwise. We go clockwise, and then we go to our linearity control. So this is kind of a game, a dance. Typically you play back and forth between these adjustments to get the raster to fill the screen. But we can increase it, but look at the stretch here. This is not right. All of the scan lines are jammed down here in one part. So this clearly isn't right either. And so if we go all the way, one full on there and full on here, when we do these kinds of things, this is what our waveform gets distorted. So as I'm turning the vertical linearity, that's fully counterclockwise. And I'm turning down, look at the frequency. So I'm turning it down all the way. So that's the frequency control turned down all the way. Let's go up, see if we can find some resemblance of where it should be. 60, 58. Well, it just starts to roll, then we haven't found our frequency. See, it just doesn't lock. Too many things going on at once. It's a question. Is that the way it's supposed to be? So we're going in right here with the scope probe. The green lead off of the vertical transformer there, and then there's a capacitor across that 0.047, and we're measuring it right there where the SAMS has it, and that's the waveform. If I had not discovered this article pretty much by chance on the internet, I never would have figured out the problems with this vertical sweep. And this particular article happened to come from the January 1962 issue of the SAMS PF Reporter, or the PhotoFax Reporter. And for those that don't know what the PhotoFax Reporter was, the reporter was published by SAMS, and it was a monthly magazine that had all kinds of articles about troubleshooting and circuit designs and new equipment and ads from vendors. It was really pretty comprehensive in all that it encompassed. And this particular article was specifically about troubleshooting vertical sweep circuits. And just the first sentence describes a great deal. There are only 4 basic vertical sweep circuits in use, and then they're listed. So effectively, every vertical sweep circuit, in that era anyway, is included in this article. And this article talks about different circuits, talks about the waveform, the vertical waveform. In this particular note, the spike that we see overcomes the inductance of the deflection coils. And in this vertical drive waveform, this section needs to be linear. It has to be linear, or you get nonlinear behavior in your sweep. So there are things that are just, invaluable information. Examples of distortion and problems and what the causes would be. But the most interesting thing about this article is that it says pretty clearly in it that if you have these problems, they have to be in this part of the circuit, because that's how the circuit works. It just breaks it down into the most important chunk of information, which is it can only be a few things. And it drives you in the right direction to go looking for something that you really weren't sure about. So I recommend this. There is actually no author credited in this, but I downloaded it from the World Radio History website. So that's the web address, worldradiohistory.com. And if you go down from the first page, the home page, and you head down here to P and Q, right away you're going to see PF Reporter Index. And that'll take you to this amazing collection of PF reporters from 1951 through, strangely, it's into 2002. I guess when they stopped publishing this magazine. But if you are interested in old black and white sets or in color sets from the mid to late 60s, there's just an enormous amount of information. So this would have been the issue that I got this article from, January 1962. And you just go to it and click on it. And there it is. And in fact, right there is our article right there, right off the bat. And everything you need to know. But you can just see the wealth of information that's included in publications like this. It is just a great walk down memory lane, and I guess you wouldn't be interested in fixing old TVs if you didn't have an interest in this kind of stuff. So start by going in here on the vertical circuit. That's what it looks like at this point. This cluster of components here and there represent a version of the integrators that I made. One of them didn't test right. The resistance was wrong. And the other one seemed okay, but I had the parts, so I made them up. They're comprised of 680 picofarad capacitors, and these two integrators have different resistance values. One is 68K, I believe, and this one is 68K, and one is what does that say? 82K. Okay, this is one of the integrators in the vertical circuit. So this signal comes from the sink amp, goes through this integrator, and then it goes into the vertical circuit. Now, this capacitor right here, a 0.022. On a modern capacitor, that would read a 223. Well, I had made the mistake way back that I replaced this capacitor with a 222. So I replaced it with a 0.002, and that was a big problem in this vertical circuit, why it just didn't work very well. I had this fold over, I couldn't get full height. That was my own fault. I did that early on in this project, and I chased my tail for a long time. Some of these resistors were off value quite a bit. This was a new electrolytic I put in there. I replaced that again, and that seemed to improve it as well. So beware of parts, even though they're new, they may not be up to snuff. The vertical circuit is working much better now, and a big part of it was my mistake. So the things that really made a difference were replacing this integrator, because let's see, where's the value of this integrator circuit is here, and these resistance value were way off. So that affected the plate circuit of this output tube. So it's this component and my mistake there that really inhibited the operation, and then this electrolytic, replacing that again, made a big difference. And then some of these higher value resistors, bias resistors, big part of it as well. So enough of that.
This may seem like a long video, but the injection itself takes about 5 minutes once you press that start button. There are also 5 words that will help you remember. All of them begin with the letter P, but I'll talk more about them later. If you have any questions or need additional help with injecting, your nurse ambassador is there for you and trained to help.